All right, everybody, this is chapter 20, quadratic functions. We're going to look at the first two sections today. There's a lot in this chapter. I happen to really like it. A lot of interesting ideas that connect to each other in multiple ways. This is the kind of thing that excites me. You should be excited too. Now, I want you to think back just a little bit. Chapter 18, we discussed exponentials. We solved exponential equations. We also did word problems. And we also saw what the graph of exponential functions looked like. Way before that, in chapter 5, we had linear equations. Those are easy to solve, right? We solved equations, we solved word problems, we also looked at what the graph of a linear function looked like. Now in chapter 12, we solved quadratic equations. We saw some word problems as well, but we didn't look at what the graphs of the quadratic function looked like. So now we're finally going to get to that. And there's going to be a lot to take in here. These graphs are certainly more complicated than linear graphs, and I think more complicated than exponential graphs as well. But by the time we get to the end of the chapter, you're going to see there are a lot of shortcuts. And as I said, the ideas connect back on each other in lots of different ways. So there's often many different approaches that you could take to work out what the graph of a quadratic should look like, or to figure out what the equation of a quadratic is based on its graph. It all just kind of depends on what information you have, what information you want to know, and whether you can come up with the most efficient way to get there. So for starters, what is a quadratic function? Well, it's a relationship which can be written in the form of y equals ax squared plus bx plus c. I like that it says it can be written in that form, because what we're going to see about quadratics is that there are actually three primary forms that we could write a quadratic. Just like with a linear function, we might write it in mx plus b, or slope-intercept form, or we might write it in point-slope form, y minus y1 equals m times x minus x1. And there is even the standard form of that, like ax plus by equals c, that I don't really think is too helpful for us at this point to worry about. Well, just like that, there's going to be a few different forms of a quadratic. This one right here is called standard form, and so that's where we're going to start. Y equals ax squared plus bx plus c, where x and y are the variables, a, b, and c are some constants, and a is not equal to 0, because if it was equal to 0, then we would really be discussing a linear function rather than a quadratic. So for starters, there's a lot of easy things that we can do with standard form. Down up here in this box, you know, if we're told an x value and we want to know what the y value is, well, we substitute the x value in and we figure out what y is. A little bit harder than that, but something that we've absolutely done before. Down here, if we're told what the y value is, we have ways of figuring out what the x value is. In fact, we had three ways. We had factoring, which is demonstrated in both of these examples. So setting it equal to 0 and then factoring. We had completing the square, and then we also had the quadratic formula. So if a problem cannot be factored, then we need to use either completing the square or the quadratic formula. Oh, or a fourth option is to just use technology, but we don't always have that handy, so these are the pen and paper techniques. We can solve quadratic word problems, and the good news is that just like exponential word problems, the function's pretty much always going to be given to you in the question. The truth of the matter is, to figure out what the equation is on your own is a lot of steps just by itself. So really that's generally just going to be its own question, and then the word problem would be its own question, rather than making you do everything all at once. If you get stuck in the first step, then you wouldn't be able to do anything. That's not really fair. So anyway, we've got this lovely function here, and it's telling us what the height is of this stone in the air, depending upon how many seconds that it's been in the air. And so this should be pretty easy to work through. Part A, we just talked about that a minute ago. How high is the stone after 3 seconds? Well, we're just putting in 3 for the t values and then figuring out what h of 3 is. So that's pretty easy to work out. Part B, well, the stone being released, that indicates that the amount of time that it's been in the air is exactly 0 seconds. So we just substitute in 0 for t. And we find out that it was released about 2 meters above ground level. That makes sense. If you're person standing up and throwing a stone, you might let go of it approximately 2 meters above the ground, depending upon how tall you are and all that stuff. And then part C, we also discussed how to do this on the previous screen. We want to know what the times, and there are potentially going to be more than one answer to something like this, where the stone is 27 meters above the ground. So 27 is the height, and then we're going to solve for t. That's a quadratic equation. We can factor this one, and we get 2 times. It's a 27 meters, both 1 and 5 seconds after releasing it. That makes sense because it was at 27 meters on its way up, and then it was at 27 meters again when it was on its way down. So its maximum height must have been somewhere above 27 meters. And that's something that we can work out later on, but not right now. So now in section B, we're discussing the graph of the quadratic. Now, the graph of a linear function was called a line, and that kind of makes sense. But the graph of a quadratic function, it's not called a quad, it's called a parabola. Lots of people pronounce that word parabola, and coincidentally, I also think a lot of people are stupid. I don't know. I don't know if those two are related, but it's pronounced parabola. Anyway, then the book has this little throwaway sentence where it says that the parabola is one of the conic sections, and it even puts that in bold. And what is a conic section? You probably have no idea. In fact, I don't think that phrase appears anywhere else in the textbook except on this one page. So of course, I'm going to take an opportunity now to speak to you about them for just a minute or two, or like 7 or whatever, because I think they're really cool. And conic sections aren't really part of the standard American high school curriculum. They don't really show up on AP or IB or SAT too much. I mean, obviously parabolas do, and some simple circle stuff does, and some simple hyperbola stuff does. Ellipse maybe on the SAT 2 exam, I don't remember, but there's a lot more about conic sections that really are not mentioned on any of these exams. And I don't know, I just think it's a really cool bit of geometry. So just to briefly explain, maybe you can see it in the picture already here. A conic section is what we get when we take a cone, or actually 2 cones, and put them kind of tip to tip, and then we take a plane and we slice through one or both of those cones. And in the first case, if the plane is perpendicular to the axes of the cones, like that, so if we could get a right angle in between that axis and the plane, then the cross section of the plane with the cone that it's going through is going to be a circle. If we tilt that plane a little bit, then we get an ellipse. If we tilt that plane even more so that it ends up being parallel with the edge of the cone, so there's a slant to the cone, and then there's how much the plane itself is slanted. So if those two are parallel, then the shape that we get out is a parabola. And if we tilt it even farther, then all of a sudden it's going to intersect with both cones, and we get something called a hyperbola. So there are equations for all 4 of these mathematical shapes, and the equations are related to each other. We're not going to get into that now, but this is why they're called conic sections, and you don't need to know any of that. I just think it's very cool how we can take these 3-dimensional shapes of the cones, slicing them with planes, and then what we get out are these nice geometric 2-dimensional things that we usually think of in terms of graphing on just a 2D plane, like the hyperbola, the parabola, and to a lesser extent the circle and the ellipse. I just think it's really neat. And so if you're interested in this, please let me know, and I can try to point you in the direction to learn some other cool stuff as well. So now we're going to start discussing the graph of a quadratic, and we're going to begin with the very simplest one, y equals x squared. And hopefully your math senses are tingling right now because you know where this is going to go. In a minute, we're going to take this simple function and transform it. We're going to translate it around the plane. We're going to stretch it. We're going to reflect it. We're going to do all that good stuff. But before we do, we're just going to take some baby steps. I want to know what this graph looks like, and we can always start by making a table of values. Just substituting in values for x into the equation, getting out our values for y, and then plotting the points. And if we do this with enough points, we might start to see some patterns occurring. For example, this particular graph seems to have a minimum value, a minimum y value specifically. The smallest y value we see is y equals 0, and it happens when x is equal to 0. We call this a turning point because graphically we can think of the graph moving from left to right as it's going down, and then it turns around and it's going up again. So that's why they call it a turning point, but we're going to call it the vertex of the parabola. Special word. We only talk about parabolas as having a vertex. More generally, it's a minimum value. We've talked about finding minima and maxima before. The minimum or maximum of a parabola is known as its vertex. Something else you're probably noticing is the symmetry in the table as well as in the graph. Any y value that we have on the left is repeated on the right. So every parabola is going to have a line, or we're actually going to call it the axis of symmetry. It's going to be a vertical line. Well, all the parabolas that we study will be oriented vertically like this one. You could draw a parabola that's sideways. You could draw a parabola that's diagonal. We're not going to be dealing with those. So for us, the axis of symmetry will always be a vertical line going through the center. That's going to come up later on though, so I won't get into that right now. Let's keep graphing. So we can always, again, this one looks quite a bit more complicated, but we can always graph a parabola by using a table of values if we need to. Eventually, I don't want us to, but if you ever get stuck, this is an option. So they tell us, go from x equals -3 to x equals +3. Well, they didn't really clarify what they want us to count by. I think we can assume that they want integer values. So we do that. We've got this down here. And we see that the turning point is going to be at -1, -4. Again, I'm just looking at the y values to see where things are repeating. And I've spotted a few of them. It's not in the center of my table, but that doesn't really matter because the table and the graph really go on forever to the left and right. So we plot the points that we came up with over here on the right and connect them with a nice smooth curve. Make it look like a parabola and all that. And we're done. There's going to be a lot going on here. Part A to this question asks us to make table of values for two quadratic functions. 2x cubed minus x minus 3, -x squared plus 2x plus 3. It asks us to graph them. I'm not going to graph them. I'm just going to deal with the table. I'll graph them afterwards. And then it says hence. Fancy word. It just means using the information you just came up with, tell me where are the values of x for which 2x squared minus x minus 3 equals -x squared plus 2x plus 3. Notice those are the same. Okay, so here's a table. Oh, and there's going to be part B. We'll deal with that in just a second. Here's a table for the first one. And I went from -3 to 3. The problem didn't tell me where to go. I just kind of used that as a guess. Hopefully this will be relevant, okay? When I look at this table, by the way, I don't see a turning point, do I? I can kind of identify where it has to be. It must be somewhere in between 0 and 1 because 18 goes down to 7, 7 goes down to 0, 0 goes down to -3, but then -3 is going up to get to -2. So the turning point must be somewhere in between the x values of 0 and 1, but I don't actually know exactly where it is. Okay, great. Now I'm going to do the table for the second one. And when we look through this, does anything pop out at you? Are we seeing this? So we've got two x values that produce the same y values in each. So the values for x for which this function equals this function must be -1 and 2. There's our graph at the left, and yeah, the two parabolas do intersect in those 2 points. So we could have also solved this equation on technologies is by graphing the two parabolas and seeing where they intersect. But otherwise, we can solve this equation algebraically. Look, it's a quadratic equation. We know how to do this. We're going to move everything to one side, simplify. In this case, we divide everything by 3, and then we check, is it factorable? Well, in this case, yes, it is factorable into x plus 1 times x minus 2, and then from there we get the two answers, that x is equal to -1 or x is equal to 2. So again, like, lots of different things going on here that all connect to each other. We've got equations, we've got graphs, we've got tables, multiple representations of a single function. I want to make sure that you can understand a function on all of the levels, all right? Okay, deep breath, because now we're going to talk about function transformations yet again. So we're transforming y equals x squared. So we're just going to think about how this is going to change. Let's talk about x squared plus k. It's going to have the same basic shape as x squared. What's the only difference? It's just moved up, right? So this is a translation where it's been moved up k units if k is positive, or down k units if k is negative. If I want to translate something to the left or right, then we're going to write it like this, x minus h squared. It's got the same shape as x squared, but it's been moved horizontally. Either h units to the left if h is, if it says like x plus a number, then it's moved to the left. If it says x minus a number, then it's been moved to the right. And generally, most books and resources, etc., are going to use these letters for parabolas. It's going to use h when we're dealing with a horizontal translation, and it's going to use k when we're dealing with a vertical translation. That just seems to be the standard notation that you'll see. So we'll use that here as well. So that's translations. Next, oh, well, okay, or we could combine the two. Great. Of course, we can do both. Next, we can talk about stretching. So this is ax squared. First of all, if a is a positive number, then the parabola is going to open upwards. It's going to look like a smiley face or the letter U. If a happens to be negative, then it's going to flip upside down, right? Just like before we had negative f of x, the entire function would reflect over the x-axis. Same idea here. And then we can talk about whether it gets wider or more narrow and stuff like that. So I don't like the vocabulary that the book is using here. I don't think they should be saying thinner and wider, because a times x squared, as we see here, that's really a vertical stretch or a vertical compression. When we stretch it to make it taller, the graph is also going to appear thinner. So that's why they said the word thinner, but I would rather us think of it as being taller. They said wider here, but I would rather us think of it as being shorter. I've discussed this before. Sometimes, if we're dealing with a simple enough function, a vertical stretch is a horizontal compression, and a vertical compression is a horizontal stretch, just depending on how you think about it. So here I've got the same function written twice. Obviously, 4 times x squared is the same thing as 2 times x all squared. On the left, I consider it to be 4 times taller. On the right, I think of it as being 1/2 as wide. But it's the exact same equation, and of course it's the exact same graph. There are just 2 different ways to verbalize the exact same thing. Putting it all together down here at the bottom, we got this form of a quadratic function. This has been moved left or right, depending upon what h is. It has been vertically stretched, depending upon what a is. And then it's been vertically translated, depending upon what k is. And this form is called the vertex form of a parabola. Earlier we saw standard form. This one is vertex form. We're going to discuss the pros and cons of each of the forms later on. But this form is called vertex form because it tells us where the vertex is on the new parabola. I'll show you what I mean in a second. So we want to sketch this graph, starting from what we know about x squared. Hence, there's that word again, state the coordinates of the vertex of this parabola. Now, once you're used to this stuff, and maybe you already know the answer, but I can tell you where the vertex is just by looking at this really fast. If you're not sure what I'm talking about, don't worry, you're going to learn that very soon. So we've got our original graph, x squared. What are the transformations that are happening to it? Well, it's getting, this minus is telling us that it's getting reflected over the x-axis. And then the other two numbers are telling us that we're moving 2 units to the right because that's a negative, and then we're moving 3 units down, again, because that's a negative. So over here in their picture, this is our original graph. It opened upwards because it was positive 1 x squared. We reflect it, and then we shift it over 2 units right and 3 units down. Where is the new vertex of the parabola? Well, it's going to be at 2, negative 3. The original vertex was at 0, 0. That vertex, where does it move? It moves 2 to the right and 3 down. So it's called vertex form because the vertex of the parabola can be immediately identified just by looking at those two numbers. Any sort of stretching or reflecting has no effect on the vertex because the vertex of x squared starts on the origin. So regardless of whether it stretches or reflects anywhere, it's just going to stay on the origin unless we move it up, down, left, or right. So if I'm ever asked to graph something like this, truthfully, I don't start off by thinking about what x squared looks like. I just look at this equation and I say, all right, it's got a negative. That means that my parabola has to have that shape. And then I ask myself, where is my vertex? Well, since this says minus 2, that means the x-coordinate's 2. And since that says minus 3, that's minus 3. The sign's going to change for the x-coordinate. The sign is not going to change for the y-coordinate. And then I just put that on my graph where it belongs. The only other information that I might want to work out is I might ask myself, what's the y-intercept? And that's easy. We just put it in x equals 0 into the equation. Easy to find. And then I might figure out where my x-intercepts are. And that involves setting y equal to 0. In this case, we would find, well, I mean, look at the picture. There are no x-intercepts. And that makes sense because in my equation, I'd be solving 0 equals negative x minus 2 squared minus 3. Let's think about this. That equation could not possibly have an answer because x minus 2 squared has to be a positive number since I'm squaring. Well, it has to be 0 or bigger at least. So then when I take a negative of that, that means I either still have 0 or I have some negative number. And then when I subtract 3 from that, there's no way that the whole thing is going to end up being equal to 0. So that equation has no solution, and that corresponds to my graph having no x-intercepts. So I'm just thinking ahead a little bit. Since we're going to be graphing quadratics, we want to be able to figure out where is the vertex, is it opening upwards or downwards, where's the y-intercept, where are the x-intercepts. Final point, and I'm going to bring this up again in a future video. So we're going to think about this again very soon. But so far I've discussed here standard form and vertex form of a quadratic function. And it'd be nice if we had a way to convert between the two of them. Well, if I have vertex form, and this is just a simple one here, if I wanted to convert that into standard form, it's easy enough. We're going to expand the x minus h squared. So that's going to give us x squared minus 2x, or let me say 2hx, and then plus h squared. And then we're going to combine that with the k. Now this, remember that h and k are just numbers, right? So my minus 2h, that's like my b. So I've got x squared plus bx. And then the plus h squared plus k, that's like my c. for a squared plus bx plus c. So converting from vertex to standard, you just expand the squared part and then combine the like terms. But going backwards from standard into vertex, potentially a little bit more challenging, but we've actually learned how to do this previously. We saw this back when we were learning how to solve quadratic equations. The answer is completing the square. So I'm not going to go through the whole process again, or at least I'm not going to spend a lot of time, but just really quickly, here's an equation in standard form. We want to convert it into vertex form. Now, if you're comfortable writing out the work like the book did here, then that's great. I personally never liked doing it this way, so I'll show it again on the next page. But what we've got here is x squared minus 4x plus 1, so that's the original. And then remember, with completing the square, you take half of the b value, so half of negative 4 is negative 2, and then you square that to get 4. So we're going to add 4 here. But if we're adding 4, we need to balance that out, so we're also going to subtract 4 at the end. Now, this whole thing here is a perfect square trinomial, x squared minus 4x plus 4. That's the same thing as x minus 2 squared. And then the 1 minus 4 gives us minus 3. So then we've converted from standard to vertex. But again, I don't really like how they showed their work there, so this is how I would have explained completing the square previously. We've got y equals x squared minus 4x plus 1. I say, first step, make sure you have 1x squared, which we do. Next step, move the 1 over to the other side. So we've got y minus 1 equals x squared minus 4x. Now, take half of minus 4. That's minus 2. Square it. You get 4. I'm going to add that to both sides of the equation to keep things in balance. 4 plus negative 1 is 3. And here I've just got plus 4. Now I'm going to factor this. That gives me x minus 2 squared. And then subtract the 3 over. The only other way that I could think of to get from this standard form to this vertex form would be to graph the function from standard form, which means either using a table of values, which hopefully works out. In this case, it would, because our vertex ends up being on an integer value of x, so when x is 2. Or using some techniques that we'll learn later in this chapter. And then that will tell you that the x value of the vertex is 2. And then you could put 2 in to this function for x, and then that'll tell you that the y value is negative 3. And then since you know that the vertex is at 2, negative 3, you can put those in here. And then, well, there's more to talk about with vertex form, but that's really not for today's video. So the point here is completing the square actually does have a nice application here. And actually, it has a lot of nice applications with the rest of the conic sections too, in particular circles. For sure, there's different forms of the equation of a circle, and to convert between them, you really want to use completing the square. Truthfully, I can't even think of a single time in my life that I've worked with too much with the equations of ellipses and hyperbolas from this perspective, so I'm not actually sure how relevant completing the square is to the two of them, but I've got a hunch that if it's relevant for a parabola, it could be relevant for a circle as well. It's just not nearly as common of a concept, so I can't speak to it right now. Anyway, that was really exciting. We got a lot of great stuff coming up in this chapter. I love parabolas. Hopefully you do too.